Hello and welcome to a very basic introduction to vectors, a very important part of our study of motion. As we've established in our last few lessons, objects move. We haven't used this term very much, but they move as the result of a force. A force is a push or a pull, and we will have many lessons about forces a little bit later on in this course. I'm introducing the idea of forces now only so I can show you a few diagrams that involve vectors, the topic for today. Please note that in these diagrams you may see forces listed with a unit of measurement called the Newton, abbreviated with a capital N. Sometimes forces also have the unit pound. That's what we use in the United States. Whenever you see a force, you will see a number. That number is called its magnitude. So for example, we may have a force of 5 newtons to the west or minus 10 newtons to the right. Notice that we had to specify a direction for the force. Direction is going to be very important because quite often more than one force can be acting on an object simultaneously. And we have to combine those forces together. So we are going to call the combination of all the forces acting on a given object as the net force. So the net force depends on the magnitude or size of forces acting on an object, as well as the directions of those forces that are being applied. Consider this diagram. We have an object which has two forces acting on it, both acting toward the right of the screen. One object has a size of 5 newtons. The other object has a magnitude of 10 newtons. We could say that there is a net force of 15 newtons toward the right of the screen. This net force is an equivalent. It is really the result of 5 newtons plus 10 newtons. But the two forces do not have to be acting in the same direction. Let's take a second case where the 5 Newton force is directed toward the left and the 10 Newton, it remains toward the right. What do you think now will happen to the object? What will it feel in terms of a net force? It will experience a net of 5 newtons toward the right. So let's look at one last example. What if the forces act in opposite directions but are equal in magnitude? We could call them equal but opposite forces. In this case, the net force is 0 newtons. In other words, 5 newtons left plus 5 newtons right equals 0 newtons overall. There is no net force. That does not mean necessarily that the object is not moving, and it certainly doesn't mean that the forces are not there. It's just that they are balanced. As we will learn in a later lesson, if there is no net force, there is no change in the motion of the object. So if it is sitting still, a net force of 0 will leave it sitting still. But if it is moving at a constant speed, then no net force will allow it to continue to move at a constant speed. Now this particular lesson is not really about force, it's about vectors. Force is an example of a vector quantity. A vector quantity is any measurement that needs both magnitude or size and direction in order to completely describe it. In our previous slides, we represented the magnitude with arrows, and we also indicated the direction with those arrows. We are going to refer to those as vector arrows, and they should represent the magnitude and direction of whatever measured quantity we happen to have under consideration. So vector arrows should be drawn to scale if you are doing this graphically, and their direction should be indicated by the arrowhead. If each centimeter is equivalent to 20 newtons of force, for example, then this vector, greatly magnified vector, arrow represents a force of 60 newtons toward the right. So just a quick recap of where we are right now. Whenever we're studying the physics of moving objects, we are going to do a lot of measuring and then a lot of calculating with those measured values. Most measurements have some sort of unit of measurement, as well as a numerical size or magnitude, such as 5 meters, 10 seconds, or 100 miles per hour. The 5, 10, and 100 represent the magnitude. The meters, seconds, and miles per hour represent the units of measurement. Some measurements have a further component, namely spatial direction. A vector must have both magnitude and direction. Some vector quantities that we have already looked at include displacement, velocity, and force. There are other vector quantities that we will run into in this course, and there are also many measurements that do not require a direction. We will refer to them as scalars or scalar quantities. Scalars must only have a size or magnitude. We've already seen distance and speed. Other scalars include things like time, mass, and temperature. Where we are headed with this is that vector diagrams, vector arrows, are often quite useful in analyzing or solving physics of motion problems. So this diagram, for example, represents the path of a projectile, such as your hoop glider. Now, just FYI, I don't plan on doing any kind of vector diagrams quite this complicated anytime soon. So vectors, vector quantities, such as force and velocity and displacement, must have a direction. Direction is very important. For the purposes of this class, we are going to use directions like north and south, east and west, or up and down, left and right. We could specify an actual degree, an angle, with respect to the origin, but many times we will be talking about some sort of linear, one-dimensional problem, in which case we will simply use plus and minus. So we are going to agree, for the purposes of this course, that if we are talking about the up and down direction only, we will call up positive and down negative. If we are talking about left and right, then we will call right positive and left negative. And that way we don't have to use a lot of complicated words. We can just indicate direction with a sign. In real life, objects can obviously move in 3 dimensions plus time. Such problems are beyond the scope of this course. We will not be doing any 3D dimensional analysis. Even in 2 dimensions, real-life objects can often move at angles other than north, south, east, and west. But a neat thing about vectors is that you can add them as our previous diagrams showed. In reverse, that means that you could look at any given vector as if it is the sum of 2 other vectors. So let me show you where we are going with this. You are no doubt familiar with properties of equality from math, such as if A plus B equals C, then C equals A plus B. It doesn't matter which way you write it. But what if those letters represented vector arrows? If A plus B equals C, then C equals A plus B. In other words, if you are given a vector like C, you can think of it as being the sum of two component vectors, even if it isn't. You can think of it as being the sum of two other vectors. Now, why would that be important? Well, let's take a step back just for a moment and look at vector C here. Describe the direction of vector C in at least three ways. Obviously, you could say that C is at an angle of 60 degrees, but you could also equally say things like it is 60 degrees north of east, or 30 degrees east of north. Or you could say something a little more qualitatively, like C is headed up toward the right-hand side of the page at an angle of 60. But what if I gave you this diagram of vector C? Now, how would you describe it? How about this? C is the result of the sum of component vectors A and B. Wow. What's the point? Even though C may not actually be the result of A plus B, we can think of it that way. We say that we can resolve vector C into two component vectors, A and B. One of those components will be along the east-west or x-axis. The other will be along the north-south or y-axis. Another way to look at this is we can take any two vectors, regardless of their direction, and add them together to get a result, or resultant is the word that we will use. A resultant is a vector that shows the result of two vectors when they pertain to or act on the same object. In other words, when we add them together. C is the resultant of A plus B. Now, I said that A and B are acting simultaneously on the same object, which we are hiding under our origin. So technically, our original diagram should have been drawn like this. Since they're both acting on the same object, they both should have the same origin. So how did they end up like this in this diagram? Well, I basically moved B over by using a graphical method of vector addition that's called the tail to tip method. And that, my friends, is the subject of our next lesson.